Okay, so first of all, I'd like to thank Professor Myoungjean for inviting me here at KAIST, and I'm very pleased to be here. So the title of my talk today is Transonic Shock and Free Boundary Problems. Actually, I want to point out that this transonic shock is a physical subject, and people started their discussion from the early 1800s. But then somehow in the middle of the 1900s, people start really understanding what this subject is. Also, mathematical study about this transonic shock has been studied very recently. So there was no much progress for the last several hundred years, but then recently there's been very interesting breakthrough. So these days people are having more interest in this subject. So since transonic shock is a physical subject, maybe it will be a good idea to just briefly explain you what this is, well, how we define this in nature, and then also I want to explain how we find the connections between transonic shock and the mathematics. Especially later, I will show you how we formulate this transonic shock problem as one of the mathematical subjects. And interestingly, it turns out that after all, the mathematical formulation of transonic shocks is given by a nonlinear PD system, and in general we know it's very hard to specify the type of the PD system. In particular, well, for the nonlinear PD system, depending on the solution itself, the system could be hyperbolic or the system could be mixed hyperbolic elliptic system. So I will just tell you the formulations in the mathematics in a minute. So another thing is that just to make this talk more interesting to general audience, I want to focus the talk in a more or less intuitive explanation about the transonic shock rather than some technical details. So if you find something unclear or confused, please feel free to interrupt me in the middle of the talk. So what is a shock? Well, in physics, well, you know what is the meaning of a shock in Korean? Well, probably the easiest way to explain the shock is a narrow region. It's not surface, it's not a curve. It has a certain volume in nature in which a drastic change of physical properties such as the density, pressure, or temperature, whatever you can define in physical space, the drastic change of such quantity happens. So that is called the shock. However, when we study the shock in mathematics, it's very hard to capture the real feature of the shock. So in mathematics, we often approximate the shock by a surface or a curve. So that's what I will show you in a minute. Okay, then the next question is, why does this shock occur in nature? Well, we can find the explanation from Stokes' description, which he gave in the middle of 1800. Well, in the middle of a discussion about whether the shock actually is possible or not, Stokes said the shock is impossible in general is because when we study fluid, we always have viscosity and heat diffusion, and those factors actually smooth out everything. Because of that, we cannot theoretically have a shock in nature. So that's what he said. But on the other hand, if we think in a different way, if the flow has a low viscosity and small heat diffusion, that will actually minimize the smoothing effect of a flow, so therefore we can observe a shock in a nature. That means that in order to have a shock, the flow usually has a low density so that the heat diffusion or viscosity can be ignored. So one of the examples we study for a shock is a gas flow. Okay, then what do we want to do with a shock in mathematics? Well, so far, most people have understood the shock through the method of experiment and numerical simulation, so we know that there is a shock. But still, it's not so clear whether this phenomenon of a shock can be uniquely defined in the nature, or whether this is a stable phenomenon or unstable phenomenon. So what I mean by stable or unstable is that, well, for certain state, when you have a shock, we start wondering whether we will have a shock or not when it's small. Well, when we perturb certain factor in a small amount. If we see a shock in that case, we say the shock is a stable phenomena. If the shock disappears, when you give a small perturbation, then we say the shock is unstable. So we want to study such, first of all, existence and uniqueness and stability by using the tool of mathematics. So that's the topic of my talk today. So before we move on to next slide, just to give you more motivations or to sell the idea how interesting this problem is, I brought a video file which is found from YouTube. So if you are interested, you can find more video like this from YouTube. Sure, but I will answer in English.
저희 공학에서 이미 부딪혀갖고 비행기는 뜨고 있잖아요. 날아다니고 있잖아요. 공학은 어떻게 해결한 거예요?
Well, as understood, they always do experiment in wind tunnel, and then by just trying a lot of cases, they just find the optimal design of the aircraft body so that the aircraft can fly in the air in the stable situations. That's how it. So basically, they do the experiment.
그러면 이 결과가 그거에 대해서 임프루브나 인디케이션이 있는 거예요?
Well, aircraft. Well, one of the reasons why we study shock is because we want to find the perfect shape so that we do not have a shock in nature. Because if you have a shock, basically that makes the motion of the aircraft body unstable. So we want to find out the shape in which case we do not have a shock. So basically, after all, we wonder when we do not have a shock. Here, what the direction of our study these days is when we have a shock. So it's just a part of understanding for the future.
혹시 그 미국에서 기계과나 항공과 같은데 교수들하고 이 통계에 관해서 얘기할 기회가 있거나 했을 때 뭐 반응이 본 적이 있나요?
Well, so far I've never experienced like that, but I hope I can in the future. So here's one of the example of the shock. It's not a transonic shock, by the way. It's just an example of shock. So here's a car explosion. When this happens, we see this 13 boundary layer just moving away from the car. So that's one of the example of a shock. Okay, so now we move on to next slide. Now, so here's the equation we want to study. So this is the mathematical method we understand the shock. So again, like I pointed out in the previous slide, we expect to have a shock when there is no viscosity or no heat diffusion. So in that sense, the equation we are studying is all the equations. If you are studying Navier-Stokes equation, you probably may notice these equations as a simplified version of Navier-Stokes equations. So this is a simplified version of the Navier-Stokes system without viscosity and heat diffusion. Then we get on all the equations. One of the ways to understand the Euler equation better is in the framework of the conservation law. And then what is the conservation law in general? So for any given spatial domain, say omega, assuming there is no external factor of the flow, so let's just say Q is a certain physical quantity. Well, for example, we can consider this as the density of the flow. Then if we integrate this on the spatial domain omega with respect to the space variable, that becomes the total mass. And also, in this case, we are looking at the unsteady problem in general. So domain is also moving by the time. Everything basically depends on the time as well. Then we can consider the time derivative of mass. And what this conservation law says is that as long as there is no external factor in the flow, the time derivative of the total mass is basically balanced by the flux of the quantity, because we can consider certain the flux of the density through the in and out through the boundary of the domain. Which is the nu is the normal vector pointing inward. So if we have positive flux, that will increase the total density. If we have negative flux, we will lose the total mass. So therefore, this is the equation of the conservation law, which is given by the integral equation in general. Of course, this conservation law must be true for any given domain omega. Then what we can do is what we can do is that by the divergence theorem, assuming that everything is reasonably smooth, well, we can rewrite this by the divergence of the flux. And on the left-hand side, like we said, the time derivative of the total mass is basically the time derivative of the integral of the density. So therefore, assuming this is true for any given domain omega, then we can actually reduce down this integral equation in the following form. So basically, this is the standard form of the conservation law. So if you look at these all equations, first the equation is a conservation of mass. Here the rho is really physical density of gas. So well, assuming total mass is basically balanced by the mass flux, we get the equation of mass. Second equation, as you see, we have the balance of momentum. And third equation we have here is conservation of energy. Here, well, we only have density and velocity and pressure. Of course, here the velocity is a vector valued function. But as you can see, from the equation of energy, we have something different, so-called E. Well, this is not a number E. This is really a function E, which is called internal energy in the physics. Well, so as you can see, the number of by just looking at this system itself, the number of equations is actually less than the number of unknown, counting E as unknown. However, if we start studying some specific type of gas, for example, today I will stick to the ideal polytropic gas, and air is actually one of the ideal polytropic gas. In that case, the internal energy is actually the function of pressure and density. So therefore, this basically closes all the system. Before I move on to next slide, in today's talk, actually, I want to point out the importance of entropy here. You may haven't heard about the entropy in many just general references. So for ideal polytropic gas, the entropy is basically the ratio of pressure and density. Here the gamma and CV and kappa, all these numbers are constant, physical constant. So basically entropy is determined by the ratio of the pressure and density. Well, what's known physically is that the entropy is something which plays very important role in study of shock. Suppose that we are looking at the particle and then we are keeping track of the motion of the particle. Then we actually have an integral curve by just looking at the velocity field of the particle. So here, x dot the time derivative of x. Then along this streamline, entropy is smooth as long as there is no shock. So shock is basically the discontinuity of density, pressure, and velocity. So if everything is continuous, it's already known that the entropy is constant. But if we start having a shock, which I will write as S today, which means that density, velocity, and pressure, which is a physical quantity, discontinuously jump across this curve or surface depending on the spatial dimension we are looking at. So if we have a shock, this is a physical entropy. If you are studying hyperbolic conservation law, there is a mathematical entropy. Now I'm talking about physical entropy. Physical entropy actually must increase across a shock. So, well, the reason why I'm saying this at this moment is because in the model I will introduce at the end of the talk today, actually really emphasize the importance of entropy in the study of shock. So we will come back to this issue in a minute. But still, well, we are all mathematicians, and mathematicians always try to simplify the problem at the beginning. Start from there, go to more complicated problem. So, PD people do that too. So what can we do to simplify this system? Because as you can see, for example, if you're looking at three-dimensional problem, which means that the velocity has three components, and you have two other functions. So you have 5 variables. You have 5 equations to solve simultaneously, which is already too bad. So one of the ways to simplify the system is to assume something which, well, hopefully does not violate the physical law that much. One of the ways is to assume that entropy is constant everywhere. Entropy is supposed to be constant along its streamline, but what we can do is to put very nice initial condition at the entrance that we can remain the entropy constant globally as long as we do not have a shock. But still, even if we are studying a shock problem, we hope that assuming these isentropic conditions to simplify the Euler system, still we want to find a shock solution which is still reasonable. But it turns out that it's really dangerous thing sometimes. So I will show you one example later. But still, so far many people have assumed that the entropy is globally constant and still get nice result. Okay, one of the special cases where this gamma is equal to 1, then we have some special flow, so-called isosomal flow. But in general, I will stick to the case where this constant gamma greater than 1. For example, air has a constant gamma about 1.4. Okay, now we can really start our discussion about transonic shock. So what is the transonic shock? So far, I only told you shock is something on which physical quantity is discontinuous. And then what do we mean by transonic shock here, and why does this matter? And then we can actually understand this transonic shock by looking at the system itself. Again, if we look at the original Euler system, this is a nonlinear system. So therefore, depending on the relation between all these unknown, well, the type of the PD system gets different. And here's the example. Just to simplify the argument, now I just want to stick to the static case, which means that our solution only depends on the spatial variable. So it's independent of time variable. And also I'm looking at the case where spatial dimension is 2, just to simplify the argument. Then actually we can rewrite this Euler system we saw in the previous slide by this way. So we have we have two spatial variables, x and y. And here u is the unknown variables. Well, in this case also I actually simplify the system a little bit by using so-called Bernoulli's law, which can be obtained again by putting the nice condition at the entrance of the flow. In that case, we have only 3 variables, and then we have this system with a coefficient matrix A and B, which are still depending on the solution itself. Then we just compute the determinant of this matrix. Then as you can see, actually one can explicitly compute that. It's really easy to compute. Then this quantity is always real, as you can see. But if you look at this quantity, we have something interesting here. So inside of the square root, we have the expression m squared minus 1. So what is m here? M is the number so-called Mach number. So you may have heard about this already, which is the ratio of the flow speed to the sound speed. So we know that, if the flow speed is faster than the sound speed, well, the Mach number will be greater than 1. If the flow speed will be less than the sound speed, we have Mach number less than 1. Then what happens? So if the Mach number greater than 1, then we call such a state supersonic. Then in this case, the eigenvalue is always real. So we have all distinct eigenvalue, which makes the Euler system hyperbolic. Then we just use the theory of hyperbolic PDE to solve this system. However, if we have the subsonic state, which means that the Mach number is less than 1, then now we start having complex eigenvalue, which means that the system is no longer hyperbolic, but this is hyperbolic elliptic mixed system. So if you rewrite the equations by looking at the eigenvectors corresponding to the eigenvalues, you can decompose this system into one hyperbolic equation, basically the transport equations, and 2 equations which forms the elliptic system. So that's what happens. So then we start having mixed system. Okay, then what is the transonic shock? We are basically looking at the case with a shock, but then before the shock, the flow speed is a supersonic, and after the shock, the flow speed becomes the subsonic. So usually I put the notation minus for the state before the shock plus for the state after the shock. So if we have a shock with supersonic before the shock and subsonic after the shock, then we have so-called transonic shock. Okay, then what does this mean in mathematics? We want to solve this PD system with a shock, but originally we don't know where this is. We have to find out the location of a shock so that before the shock we have hyperbolic system, after the shock we have elliptic system. Of course, to have such a phenomena, also we have to describe appropriate condition at the entrance so that we can have a supersonic flow before the shock. But anyway, so what we have to do to find the transonic shock is to solve this system and find the location of this shock, which actually is interpreted as a free boundary in the study of PDE. What I mean by free boundary, when you solve a PD, for example, say Laplace and Poisson equations, then you need a boundary conditions over here. But then now we are basically looking at the case where this boundary is undetermined. So that is called the free boundary. Okay, well, of course, one can still consider the case where the state both behind in front of the shock is hyperbolic. Then you have supersonic shock. So we have two types of a shock, either supersonic or transonic. But one has to know that there is no subsonic supersonic shock because that violates the entropy conditions. As I pointed out earlier, entropy always must increase. So mathematically, theoretically, it's possible to have subsonic supersonic shock, but that's not admissible in physics. So we exclude that case. And also, there is no subsonic shock because the regularity theory of elliptic system. So we only have two cases. Now, again, I'm always trying to sell the idea that shock is something cool. So here's one of the examples to draw your attention. So we see this aircraft, which is F-18, and when the speed of the aircraft is reached about Mach number 0.8, the speed is still subsonic, but then we know that the aircraft body is curved surface. So somewhere on the body of the aircraft, the flow air speed reach to the supersonic, then you start seeing the transonic shock. So you see this cloud formed around the aircraft body, which is basically the shock because the air is pressure, very high density. In front of the shock, the state is supersonic. And behind the shock, the flow speed drops down immediately, then you have subsonic state. So this is one of the examples of transonic shock. And well, studying this problem theoretically is still wide open though. Okay, so far now I really start giving you the idea that we really are looking at the solution of a PDE with a discontinuity in the middle, which doesn't make sense theoretically. You're looking at the PDE, which actually assumes that the solution is differentiable. But we are talking about something, the solution with a discontinuity somewhere. So what does that mean? Well, it doesn't sound so nice, but we have to remember that the conservation law is given by integral equation at the beginning. So actually we have to go back to the integral formulations. So one of the natural ways to define the shock solutions as a solution to all the equations is to look at the weak formulations. So we define, still I'm talking about static case, but one can actually follow the argument in the parallel way to talk about still the original unsteady Euler equations. So again, but for simplicity, I will stick to the steady case. So we say these functions is a shock solution. So let's just talk about shock solution for now and then worry about transonic later. So we say these functions is a solution, the shock solution to Euler system if, first of all, it satisfies the weak formulation of the Euler equations for any given smooth test function. This is, well, if you are studying the PD, well, this is also one of the natural way to define the solution with a low regularity. And then the second conditions, well, here nu is the normal vector to the shock, pointing to the state behind the shock. Then we are talking about normal velocity on the shock. So the solution has to satisfy this condition, which implies that the normal velocity must drop down across the shock to satisfy the entropy conditions. So somehow this is the jump condition. So if the solution satisfies these two conditions, when we have a shock solution to the Euler system. Moreover, like I said earlier, if there is the drop of Mach number from the greater than 1 to less than 1, then we have transonic shock solutions. Okay, so how do we solve to satisfy all the conditions of the definitions? Well, but still we need a certain regularity. As you can see, we are talking about normal vector to shock, so we need a certain regularity. But we know that if we are looking for the solution with a discontinuity across a shock, but then if we just allow that the solution is reasonably smooth in each of smooth region, then by looking at by manipulating, basically by using the integration by parts, you can find out that this condition is basically equivalent to the following, which means that these functions satisfy the Euler equations pointwisely in each of smooth region. Plus, this is the jump conditions. So here, when I say the bracket of a function f on the shock S, that means that if my function is basically continuous in each of the region, I can take the limit to the shock from the both sides. So therefore, I can take the difference. So this jump condition actually coming from basically integration by parts, because if you do that, you have a boundary integral term. And from there, you can actually derive this condition very naturally. So we have where normal mass flux normal density flux must be balanced out. And here B is the so-called Bernoulli's invariant. So Bernoulli's invariant is supposed to be continuous across the shock. And there is also the normal momentum flux on the shock. It must be balanced out. So what we do is to somehow manipulate this jump condition algebraically, so that some of these conditions are used as a boundary condition of the PD in each of smooth region, plus some of the conditions must be used to determine the location of a shock, which is a free boundary. So some of them is a free boundary conditions, and the other becomes just the normal standard boundary condition of the PDE. So we use this definition to study the shock solutions. Now, I will not go into technical detail from now on. Just again, I'm trying to sell the idea. This is something you really want to study in the future. But I will show you two examples. First example is the solution of unsteady Euler equations, so-called the shock reflection problem. And I brought two different pictures. So if you look at the pictures on the left, you notice that the angle of the wedge is relatively big. If you look at the pictures on the right, the angle of the wedge is small. So here is a shock which is already formed somewhere far away from this wedge. And we are looking at the case where this shock is moving toward the wedge. And then you will see that there are two different phenomena happening around this wedge depending on the angle of the wedge. So on the left, if we have a large angle wedge, then we see the shock somehow hitting on the boundary of the wedge, and then there's a curved shock which is basically reflected by this point. And this curved shock is actually start moving away from the wedge. And you also notice that even though this is the unsteady problem, the shock has certain symmetric pattern. After all, recently people found out that this actually becomes self-similar solution. So I will show you the result in a minute. And this is called a regular reflection. So very natural. The shock is hitting the wedge and then the shock is reflected. Of course, inside of this region, something non-trivial is happening. And also, I have to mention that here, a part of the curved shock is a supersonic. The other part of the shock is a transonic shock. So somewhere in between, or there is something interesting happening. I will come back to that in a minute. The other case is so-called Mach reflection, which is still completely open. So when the wedge angle is sufficiently small, the shock basically is reflected, but the reflection happens away from the boundary of the wedge. And then we see that there are two shock reflections. One is actually moving away from the wedge. The other is actually is basically normal to the boundary of the wedge. And then there is a very well-known fact that we cannot have three shocks at one point. So because of that, in the middle we have a so-called vortex shear. So what this is that across this curve, the normal velocity of the flow is continuous, but then tangential velocity is different. So what happens is that across this, some state has this much tangential velocity, some other state may have a different tangential velocity. So you have so-called vortex shear. So still, we don't know how to find out the exact location of this reflection point, or also how to find this reflection shock plus this vortex shear. Some people call it contact discontinuity. Okay, so to convince you, well, all this phenomena happens in the self-similar pattern. Again, here's another video file I found from YouTube. This is not the simulation I made. This is something I found. So here we see that maybe we should ignore the picture on the right. I don't know what this is, but here when the shock is happening, shock is hitting the wedge. And then we see this reflection, and then this reflected shock is again moving away from the wedge, well, roughly in a self-similar pattern. So people believe that there would be a self-similar solution. And then the proof is given very recently. Well, I will just show you the results by Feldman, which is my thesis advisor, and Myoungjean. But before that, actually, there's been some study by using different model. And then in the recent result by Feldman and Chen, they used the so-called isentropy, which means that the entropy is globally constant. Physically, this is not true, but again, this is still gives us good idea about the solution in general. Plus potential flow, which means that we assume that the flow is irrotational, which means the curl of the velocity is 0. So therefore, we can actually replace velocity vector field by the gradient of some function, which is called the velocity potential. But then they expect the solution would be in the following form. So here, like I said, we expect the solution in the self-similar pattern, which means that the solution will be given by a function of the variable x over t. So here x is a spatial variable, which is in this case they are looking at R2 case, the two-dimensional case. And then in this case, the Euler system is amazingly reduced down in the second order nonlinear PDE like this. And also, like I said here, the reflected shock is consisting of two parts. One is the straight part, which actually, well, amazingly, it's very easy to compute the location of a shock plus the state behind it, because the state behind this straight shock is given by the constant density. Well, again, I showed you earlier the Rankine-Hugoniot condition, jump conditions, so one can explicitly solve this algebraic relation. In this case, of course, one has to be a little bit careful to apply implicit mapping theorem, but still one can explicitly compute this state as a constant state. But then the question is what happened behind this curved shock. And it turns out that, well, there is some reason why we cannot have one type of a shock. Actually, this should be transonic shock, which actually one can understand from this state. So, well, people did not know the state behind this curved shock. Moreover, well, since there is a change of the type of a shock in between, behind this results, there is some gradual change of the flow, the type of the flow. So here, the flow is supersonic. Here, the flow is subsonic. But this is not a shock. everything is changing continuously, which means that somewhere in between the flow state becomes sonic. And this is bad news to the people who study PDE because that makes the equation, well, here in the state 2, this equation is strictly hyperbolic, which is fine. Away from this curve here, the equation is strictly elliptic, which is okay. But now, exact on this curve, which actually one can compute, actually this becomes a part of a circle. Over here, the equations, the type of the equation becomes degenerate. From this side, this becomes hyperbolicity degenerate. From this side, ellipticity degenerate, which makes it very difficult to study the PDE and so find the solutions. So now, but even so, they somehow found the solutions by using very technical method. So, and then the first result, they proved the existence of solution for the really sufficiently large wedge angle, almost 90 degrees. But recently, actually, they also proved that there exist self-similar regular reflections up to all the angle. What I mean by all the angle is reasonably large angle, because if the wedge angle is small, then you actually start seeing the marked reflection. So right before that, you can always find the self-similar solutions. And now what we study actually in the collaboration with Chen and Feldman in a separate paper is what happened near this curve. Because near here, this equation, we study from the elliptic side. So what we found is the following. Well, but this doesn't actually look very interesting. So let me go back to the slide and just explain what this means. So first of all, we show that even though this equation becomes the ellipticity becomes degenerate, we show that velocity is smooth. Well, smooth. Well, strictly speaking, we'll see 2 alpha for anywhere the exponent alpha between 0 and 1. Then once you have this regularity, you have smoothness as well. But anyway, away from this point is something different. Up to this way, solution is always smooth, which is a new result because the ellipticity is degenerate. So actually there was no general result. So we found this regularity theory. But physically speaking, what happens is the following. This is not a shock, so therefore velocity is continuous across this curve. But what we found is that even though the velocity is continuous, the derivative is not continuous. So we found that, well, we classify such discontinuity as weak discontinuity. So velocity is continuous, but the derivative jump. And then we were actually able to compute the difference of derivative very explicitly. It turns out that, well, I did not point out here, but it turns out that the jump depends on some physical constant, so-called gamma. One more thing is at this point, which is the intersection of the so-called sonic curve and the shock, velocity, the first order derivative of the velocity is different. So if you approach it from here, the velocity has certain value. If you approach it near from the shock, then you have different value. So basically, there is also velocity is not even C1 at this point. So this somehow contains certain optimal regularity theory plus a physical meaning of the shock reflection.
By the way, who is E.H. Kim?
Uni Kim at I think Southern California State University, yes. So Uni, she worked with Kifich and Chenich and Riverman, and then she also worked something on this with a different model, yes. Okay, so this is the example of unsteady case. Now, here's another example of a steady case. What do I mean by the steady solutions? I'm basically looking at the solutions, which is basically the asymptotic limit of unsteady solution when the time goes to infinity. So one of the examples that I studied is the so-called the flow in the de Rayburn nozzle. So this indicates the first half, the upper half part of the nozzle we are looking at. The entire picture is like this. And then we are studying the gas flow inside of this nozzle. And then interestingly, what happens is inside depends on actually the pressure you put at the exit of the nozzle. So if, well, for example, if the pressure at the exit is sufficiently large, that means, well, basically that means there is no one interrupting you inside of the nozzle. So you are free. So you can run as fast as you can. So therefore you have a very fast flow. So here, if well, the pressure, the high pressure, which means that you have a slow flow. So upper this line, you have subsonic state. Below this line, you have a low pressure, which means that the velocity is very fast. So you have a supersonic state. So if you put sufficiently low pressure, well, you see that the just flows in terms of flow speed, the speed is getting faster and faster and faster. But if you put certain level of the pressure shouldn't be too high, then you completely block. So if the pressure at the exit is at a certain level between these two curves, then let's see what happens. In this convergent part, well, the pressure is decreasing, which means that the pressure is getting accelerated. But when it reaches to the throat of the nozzle, then something different happens when you put the exit pressure somewhere here. Well, when the flow reaches to the end, well, the pressure of the flow must be equal to the pressure at the exit. Well, to be able to let that happen, the only option from this graph is that there must be a jump of the pressure, which means that there must be a shock. Also, moreover, and in this case, we see that the velocity jump, the jump down from the supersonic state to the subsonic state, that you have a transonic shock. So this also is one of the examples of transonic shock problem. Again, to convince you, well, we really have to see what happened for the static case. This is the simulation, again, found from YouTube. Here the blue color is a low Mach number, which means you have a subsonic flow. The red color is high Mach number, you have a supersonic flow. So when the flow starts, you see that it's getting accelerated, but at a certain point the speed must drop down so that you can have you can match the pressure at the end, and then so therefore we can expect some steady solution at the end. Okay. So what I studied is the flow in this divergent part. The flow in the convergent part, again, wide open problem, because now, again, one has to see this sonic region. Then you have, again, degenerate PD, which is very difficult to study. So this is also one of the interesting problems to study in the future. Okay, so here, this is the picture I studied. So what I wanted to do is to look at the arbitrary cross-section, because what people have done so far is to study the multidimensional flow is to assume certain symmetry of the cross-section. One of the example is that in the work by Pravo, Juping, Shin, and In, they nicely study three-dimensional Euler system, but the problem is that they assume axis symmetric solution, which means that where basically your solution depends on two spatial variables, then you can reduce down the system to two-dimensional Euler system. So still, well, there was no result about the general cross-section. So I wanted to study that case, but then still it was very difficult to study with the entire system. So I wanted to study potential flow first, but then interesting thing happened. Well, before I explain you what's interesting, let me just tell you the model I studied. So here, well, I'm assuming the potential flow model, which means, again, velocity is basically the gradient of a scalar function. So the first equation is a conservation of mass. This equation is basically conservation of energy, which is somewhat simplified in this case by just putting the nice condition at the entrance. Now the third condition is something different. Without this part, this is simply conservation of momentum. But then again, we have less number of unknown, so it doesn't make sense to count in the entire system. So I have to somehow only count in the conservation of momentum along the streamline, which means that I only look at the conservation of momentum along the trajectory of the particle. Okay, then what's new here? So far, in the study of potential flow, people only study this equation. What they did is to assume, again, isentropic conditions. So for the isentropic potential flow, I have to say that everything, density and pressure, they only depends on the speed squared. What is the isentropic case? We only assume that this is a constant k. Then everything only depends on the speed. So that is the mode that people have been using so far. But in this case, we cannot do that. And here is why. So that's why I actually emphasize the importance of the entropy at the beginning. So if we assume the isentropic potential flow model, what's nice is that you only have one equations of potential. So it's very easy to study. But then what's the problem? That everything else only depends on the speed. Okay, well, so far it worked out nicely, many other problems. But when you have this divergent nozzle, something very uncomfortable happening, and here's why. Now, for simplicity, suppose that you have a constant pressure. But then you can expect to find the solutions only depends on the radial variable. If that is the case, your PDE becomes the ODE. So it gets very easy to analyze. When we do that, what happens is the following. Well, suppose that you put a shock somewhere here. Also, suppose that you put, that's one solution. Also, let's consider another solution with a different location of a shock. And for this isentropic case, interestingly, the pressure at the exit is already same, regardless of the location of the shock. So what does that mean? That means that either you have infinitely many solutions if you put an appropriate pressure at the exit, or you have no solutions. So this is ill-posed. And what's wrong with this solution is because where you assume the entropy is constant, which it shouldn't be. So therefore, so far, when people study so-called flat nozzle, geometry actually doesn't see the difference. So it was okay. But again, actually they had to put certain restriction to find the uniqueness. But here it's really the isentropic condition caused real trouble. So we couldn't use the original nice isentropic potential flow model. So I had to actually count in this part. This part is basically somehow gives us more information about the entropy. So, well, this system looks very bad, but after all, you can somehow decompose in this way, but then you have still the same equations as isentropic potential flow model, and what's newly added is these transport equations. So once you find the solution from these equations, and then you can just simply solve these transport equations to find out pressure P. This entire term is the entropy. Okay, but the issue is not just adding the equations. When you do that, which means that now actually we start saying that pressure is something independent. It does not depend on speed anymore. It still depends, but it's not completely depends on the speed. It's something different. It's something independent. When we do that, actually we also have to look at the Rankine-Hugoniot conditions more. For the isentropic potential flow model, people only can add the Rankine-Hugoniot condition from the conservation of a mass, and then this continuous condition, which basically means that we exclude vortex shift from our shock. That was the only two conditions we can have for the isentropic case. But when we start allowing that the pressure is independent unknown, then we are allowed to have all the jump conditions from the original Euler system. That means we allow the jump of entropy across the shock. Okay. So therefore, now we really start seeing that the entropy is something important. So by using this new model, we were able to first of all prove the existence in the following sense. For if we put the constant pressure, then everything becomes ODE, so you have explicit solution. Now we are wondering what happens if we put small perturbation of the constant pressure. Then what we proved is the following. Again, we also need a certain boundary condition at the entrance to have a shock. So when you put the boundary condition for supersonic flow, when you put certain small perturbation of a constant pressure here, then there exists a unique location of a transonic shock, so that you can find a supersonic solution and subsonic solution satisfying our so-called non-isentropy potential flow model. And also, we have stability reserved. The difference between the so-called background solutions, which is the solution of a constant pressure, and this is the solution for the pressure with the small perturbations. The difference is basically well controlled by the perturbation of the exit pressure. But then what's interesting is that, well, again, I put some regularity conditions. So here, basically, it's okay to put any small perturbation of a constant pressure. This is a paired exponent. So I'm basically looking at the C alpha perturbations. For any world exponent, I can find a solution. Now, why do I not have uniqueness at this point? It's because of the transport equations. In seeking the uniqueness of a solution, now we are basically looking at the system. So we also have to look at the uniqueness from the transport equations, but then the regularity somehow causes a trouble. What I can do, though, is if I raise the regularity a little bit, then I have the uniqueness. Okay, it doesn't sound so interesting, but actually what's more interesting is these transport equations and the result we have here. Well, this is the entropy. I will simply replace by something simpler. Here is generally how we solve the transport equation. This is probably can be understood by any mathematicians. Suppose that given the velocity field, I want to find out E satisfying this condition. Then what we do is the following. I solve this OD system, then with certain initial condition, then this integral curve x, solving this equation, give so-called a streamline. According to that, our solution epsilon can be just simply given by this. What I mean by that, if I know the value of the E here, then the solution value is remain constant along its characteristic. So therefore, solving the transport equation only reduces down to solving this OD system. That is how we generally solve the transport equations. But then what do we need? We need a certain regularity condition. If you have taught OD class, right? To have the solution of this, we know that to have not just a solution, you need a unique solution. We know that at least we need this, Lipschitz condition. But for our case, because of a certain regularity of the solution of elliptic equations, our solution is not C01. Our solution is only C0 alpha, which with alpha less than 1. So we do not have usually uniqueness. But then, using some local argument of the regularity theory of elliptic equations, actually we were able to show that the second derivative of potential, you can consider this as a first order derivative of velocity field. Somehow, it's not the derivative of velocity field blows up somehow near the boundary, but then it blows up by a certain speed, which is some speed that we can control in integral formulations. So by using these formulations, we were actually able to basically solve this OD system for somehow weak regularity velocity field. So this is something new from this work. So this was the joint work with my thesis advisor. Okay, so where do we want to go with this? Well, still, for the steady problem, three-dimensional full Euler equations completely open. We don't know what to do in general domain. Also, I mentioned about subsonic sonic flow. In this convergent part, we still want to find out solutions. And then for the unsteady case, well, I show you the regular reflection for the potential flow. Full Euler equation still, it's very difficult, and here's why. When you look at the full Euler equations, now you really start considering the vorticity of a flow. For the regular reflections, we know that there is a point where the velocity vanish, which makes the vorticity blow up. So this is one of the difficulty why we do not have any result, and Mach reflection completely open. For the steady problem, well, for the usual regular unsteady Mach reflections, well, there is no hope yet, but then we hope to get some result for steady case, and just to understand the structure of the Mach reflection, and then probably move to the general Mach reflection problem. So this steady Mach reflection, there's a partial result, but still, it's not completely understood in the unbounded domain. So that's one of the problems that I'm studying right now. And then also, the second problem I show you, I look at the case where the small perturbation of the straight nozzle. If it's curved in an arbitrary way, still there is no way, there is no solution known clearly. So main point is still there are a lot more problems to explore. So I will be very happy if some of you are interested in this problem in the future. Okay, thank you for your attention.